Welcome to Mrs. Beck's read-along on Concept 10, Recursion. So in this concept, the concept's going to be defined and explain exactly what recursion is. It's also going to show how to read and trace the recursion method, which is really important because reading and tracing is going to be on the AP exam. I don't know what this means. Okay. Key ideas. A recursive method is a method that calls itself. Recursion is not the same as a nested loop or while loop. A recursion method must have a base case that tells the method when to stop calling itself, and you will need to know how to trace a recursive method on the AP Computer Science A exam. You will not have to write a recursion method. So first we're going to go over recursion versus looping. The for loop and the while loop allow programmers to repeat a set of instructions. Recursion is the process of repeating instructions also, but in a self-similar way. I know that's kind of weird, so let me explain that by using the following example. Example 1. Imagine you're standing in a really long line and you want to know how many people in line are in front of you, but you can't see everyone. If you ask the person in front of you how many people are in front of him, and he turns to the person in front of him and asks the person in front of him how many people are in front of him, and so on, eventually the chain reaction will reach to the first person in line. That person will turn to the person behind them and say, no one. Then something fun happens. The second person in line will turn to the third person and say, one. The third person will turn to the fourth person and say, two, and so on, until finally the person in front of you will respond with the number of people who are in front of him. This creative solution to the problem is an example of how a recursive algorithm works. Recursion is a programming technique that can be used to solve a problem in which a solution to the problem can be found by making subsequently smaller iterations of the same problem. When used correctly, it can be an extremely elegant solution for a problem. One method can call another method, right? What if the method called itself? If you stop and think about that, after the method was invoked the first time, the programmer would never end because the method would continue to call itself forever. Think of the movie Inception. Example 2. Here's an example of a really bad recursive method. You've got public static void. We're going to call the method I'm a bad recursive method with the parentheses because it's a method. It's got parentheses. And inside that method, it just calls I am a bad recursive method. This means that the method never stops calling itself. However, the method had some kind of trigger that told it when to stop calling itself, then it would be a good recursive method. So the general form of a recursive method would be public static and then the return type. Good recursive method, we'll call this, parentheses with the parameters inside. There would be an if, and in that if clause would be the base case is true, and it will return something. Else, then it would return the good recursive method doing it over and over again. Note, all recursive methods must have a base case. The base case. The base case of a recursive method is the comparison between a parameter of the method and a predefined value strategically chosen by the programmer. The base case comparison determines whether or not the method should call itself again. Referring back to the example in the introduction of this concept, the response by the first person in line saying no one is the base case. It is the answer that reverses the recursive process. Each time the recursive method calls itself and the base case is not satisfied, the method temporarily sets that call aside before making a new call to itself. This continues until the base case is satisfied. When there's finally a call to the method that makes the base case true, the base case is satisfied, the method stops calling itself and starts the process of returning a value for each of the previous methods called. Since the calls are placed on a stack, the returns are executed in reverse order of how they were placed. This order is known as last in, first out, LIFO, which means the last recursive call made is the first one to return a value. Furthermore, each successive call of the method should bring the value of the parameter closer and closer to making the base case true. This means that with each call to the method, the value of the parameter should be closing in on making the base case true, rather than moving further away from it being true. If a recursive method does not contain a valid base case comparison, then it might continue to call itself into oblivion. That would be bad. What do I mean by bad? Remember, every time a recursive method is called, it is set to call aside temporarily until the base case is satisfied. This process is called putting the call on the stack. And in the computer stores, the stack is its RAM. If the base case is never satisfied, then the method calls pile up and the computer eventually runs out of memory. This will cause a stack overflow error, and it occurs when you have infinite recursion. Note about the base case. The base case is a comparison between the parameter of the method and some specific predefined value chosen by the programmer. When the base case is true, the method stops calling itself and starts the process of returning values. Every recursive method needs a valid base case, or else it will continue to call upon itself indefinitely, infinite recursion, and cause the out-of-memory error called a stack overflow. Beginning example, the factorial recursion method. A very popular problem to solving using recursion is the factorial calculation. The factorial of a number uses the notation n exclamation point, and it's calculated by multiplying the integer n by each of the integers that precede it all the way down to 1. Factorials are useful for computing combinations of permutations when doing probability and statistics. For example, to find the answer of 4 factorial and 10 factorial. 4 factorial is really just 4 times 3 times 2 times 1, which is 24. So therefore, 4 factorial is 24. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5, all the way down to 1. And therefore, it's a huge number. Why the factorial calculation is a good example of recursive? The definition of factorial can be written recursively. That means the factorial of the number n can use the factorial of the previous number n minus 1 in its computation. So n factorial is really just taking that n number timesing whatever the answer of n minus 1 factorial is, where 1 factorial is defined as 1. So if we look up at this example of 10 factorial, it's the same thing as saying 10 times whatever 9 factorial was, right? Because 9 factorial would have been 9, 8, 7, 6 times, so on and so forth. So that's why you can write recursively like this. So here's the example. Write 4 factorial recursively using math. When you start to compute 4 factorial using the definition of factorial, you see that 4 factorial is 4 times 3 factorial. This means in order to compute 4 factorial, you need to figure out what 3 factorial is. But 3 factorial is 3 times 2 factorial. So we have to figure out what 2 factorial is. And 2 factorial is 2 times 1 factorial. And 1 factorial is 1. Do you see how we had to put our calculations on hold until we got to 1 factorial? Once we got the final answer of 1 for 1 factorial, then we're able to compute 4 factorial by working backwards. So if you look at this kind of calculation table, you see that you first write 1 factorial equals 1. So that means then 2 factorial equals 2 times 1 factorial. But we know 1 factorial is 1, so then we could do the 2 times the 1 to get the 2. 3 factorial, we already said before, was 3 times 2 factorial, but we didn't know what 2 factorial was until we did the calculation above that and found out that 2 factorial, in fact, was 2, so that's when we get 6. We noticed before that 4 factorial was 4 times 3 factorial, but we didn't know what 3 factorial was until we just did the calculation above when we found out what 2 factorial was and 1 factorial was. So 3 factorial ends up being 4 times 6 factorial, which equals 24. So implementation of the factorial recursive method, looking in Java. So you would just do public class factorial, public static void main string args, you know the deal. System.out.print factorial 5. So that means find factorial 5. So this is a recursion method that computes a factorial number with parameters finding the factorial of the number in the parenthesis. Precondition, we need to note that n greater than or equal to 1, and the result of the recursive call in the factorial of the original argument. So this would be the little method. public static int factorial, and then you plug in that int n. If n equals 1, then we're returning 1. So that's our base case. That's saying basically 1 factorial is going to be 1. Again, equals is the comparison. It's not setting n equal to 1. That's just with 1 equals. Else, it's going to return n times and then factorial n minus 1. So that's invoking the factorial method within the factorial method. That would be the recursion section of this. And it moves closer to the base case. And then for this, you should shoot out 120 because that's what 5 factorial is. Good and bad news. On the AP exam, you will never be asked to write your own original recursive method. However, you will be asked to hand trace recursive methods and state the results. So how does this hand tracing of the factorial method look? This is kind of tricky, so read it over carefully. When tracing a recursive method call, write out each call to the method, including its parameter. When the base case is reached, replace the result from each method call with its result one at a time. This process will force you to calculate the return values in the reverse order from the way the calls were made. So remember, our goal is this problem to compute the value of factorial 5 using the process of recursion. So step 1, this problem similar to find the number of people in line example. The answer to the factorial requires knowledge of the factorial preceding it. Suppose I ask the number 5, hey, what's your factorial? 5 responds with, I don't know, I need to ask 4 what its factorial is before I can find my own. Then 4 asks 3 what its factorial is. And then 3 asks 2 what its factorial is. Then 2 asks 1 what its factorial is. At that point, then 1 says it's 1. So after 1 says it's 1, the process reverses itself, and each number is able to answer the question that was asked of it. The answer 1 is the base case. So therefore, then 1 can say my factorial is 1. So 2 says, then my factorial must be 2 because 2 times 1 is 2. Then 3 will say my factorial is 6 because 3 times 2 is 6. Then 4 says, oh, my factorial is 24 because 4 times 6 is 24. And finally, 5 turns to me and say, my factorial is 120 because 5 times 24 is 120. So again, here's how it looks if you hand trace it. The first step is writing the factorials in order with just that factorial method written in. Then once you find out the base case, then you can rewrite the base case in where it says factorial 1. And you can write the 1, which means then you can rewrite for factorial 2, which means you can rewrite for factorial 3 and factorial 4. For hand tracing recursion methods, you do need to write a lot. You need to write out this process the way up and the way down. You're going to take up a lot of space writing it. Don't think you can get through a recursion problem without hand tracing and writing a lot. So here's a visual representation of computing a recursive method. Example, explain how to compute the value of 5 or factorial 5 for the visual learner. As you trace through this problem, think of the example of the people in the long line. If I were you, this is how you should write your process for hand tracing. You start with the start, you're finding factorial 5. So you know factorial 5 must be 5 times the method of factorial 4, which is then 4 times the factorial of 3. 3 times the factorial of 2, 2 times factorial method of 1. Once you see that, you know that the return is 1. So now you're going to fill in the right value for each of the factorials that we're missing. So you're going down and then back up to the finish. Here's a little more an advanced example. This is the Fibonacci recursive method. On the AP exam, you will need to be able to hand trace recursive method calls that have either multiple parameters or make multiple calls within the return statement. The following example shows a recursive method that has multiple calls to the recursive method within its return statement. So the Fibonacci sequence is a popular sequence, and it's also often covered in math class as some interesting applications. In the Fibonacci sequence, the first 2 terms are 1, And then each term starting with the third term is equal to the sum of the two previous terms. So it's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. See how the 1 plus the 1 equals the 2, and then you get the 3 by the 2 and the 1. You get the 5 by the 2 and the 3. You get the 8 by the 3 and the 5, so on and so forth. So the Java code that's provided below is the recursive method that returns the value of the nth term of the Fibonacci sequence. Example, Fibonacci 6 is equal to 8. The value of the sixth term is 8. So as it would be on the AP exam, you would see the recursion method written out. So in this case, it's looking at Fibonacci of 6. It's saying that the Fibonacci method looks like this. If n is equal to 1 and n equal to 2, return 1. So it's saying at the first case, n is 1, and at the second case, n is 1. If that's not the case and n is not 1 or 2, then we were recursively calling the Fibonacci sequence over and over again, and you're doing n minus 1 plus n minus 2. And you should get the output 8. So how to hand trace this? This is harder to follow than the factorial recursive method because the return statement includes 2 calls to the recursive method. And there are also 2 base cases. So goal, compute the Fibonacci sequence of 6. In a manner similar to the previous example, I asked 6, what's your Fibonacci? 6 responds by saying, I don't know now. I need to ask 5 and 4 what their Fibonacci's are. And in response, 5 says, I need to ask both 4 and 3 what their Fibonacci's are. And 4 says, well, I need to ask 3 and 2 their Fibonacci's. This continues until 2 and 1 are asked what their Fibonacci's are. Ultimately, 2 and 1 will respond with 1 and 1. And each of those numbers can then answer the question that was asked of them. The 2 and the 1 are the base cases for the problem. So if you see, then 1 and 2 are equal to 1. So all of those Fibonacci 2, Fibonacci 1, we fill in 1 and 1. So Fibonacci knows now that he's 2. And so since Fibonacci 3 knows that he's 2, Fibonacci 4 knows that for Fibonacci 3, she can put 2 in. And for Fibonacci 2, she can put 1 in, getting 3. So now Fibonacci 4 knows what she is and tells Fibonacci 5, hey, dude, I'm 3, so fill 3 in for me. Fibonacci 3 was 2, so that means Fibonacci 5 must be 5. So then Fibonacci 5 will go tell Fibonacci 6, hey, I was 5. Fibonacci 4 was 3, so 5 plus 3 is 8. And that is how to do recursive method.